When feeding a 400 amp motor control center from a panel board with a 480 volts alternating current supply, several factors must be considered to ensure the installation complies with the National Electrical Code and operates safely. The proposed plan involves a 200-foot conduit run with two 4/0 conductors per phase and one number 3 ground wire in a 4-inch conduit. The primary considerations are ampacity, derating due to multiple current-carrying conductors in a single conduit, and appropriate conductor sizing. Firstly, let's address the conductor ampacity. According to the National Electrical Code Table 310.16, a single 4/0 copper conductor, when rated for 90 degrees Celsius, has an ampacity of 260 amps. Since the plan involves using two 4/0 conductors per phase, the combined ampacity before derating is 520 amps. Secondly, consider the derating requirements specified in National Electrical Code Table 310.15 V3A, which is now National Electrical Code 310.15 CON. When there are more than 3 current-carrying conductors in a raceway or cable, the allowable ampacity of each conductor must be reduced. In this scenario, there are 6 current-carrying conductors, 2 for each of the 3 phases within the 4-inch conduit. Consequently, an 80% derating factor must be applied. Applying the 80% derating factor to the combined ampacity of the two 4/0 conductors per phase results in a derated ampacity of 416 amps, calculated as 520 amps multiplied by 0.8. This derated ampacity of 416 amps exceeds the 400 amp requirement for the motor control center feed, indicating that the two 4/0 conductors per phase are sufficient to handle the load after accounting for derating. Thirdly, selecting an appropriate conductor temperature rating is critical. The 90 degrees Celsius rating of the 4/0 conductors is essential to utilize their full ampacity potential. If conductors with a lower temperature rating, such as 75 degrees Celsius, were used, the ampacity would be lower, potentially requiring larger conductors to meet the 400 amp demand after derating. Additionally, the equipment termination temperature limitations, as specified in National Electrical Code 110.14c, must be considered. Conductors must be selected and installed such that the temperature rating associated with the termination is not exceeded. This typically means using the 75 degrees Celsius ampacity column in National Electrical Code Table 310.16 for equipment terminations rated for 75 degrees Celsius or less, unless the equipment is specifically listed and marked for use with 90 degrees Celsius conductors. In many cases, the 75 degrees Celsius ampacity will govern the conductor selection, even if the conductor insulation is rated higher. Fourthly, ensure that the number 3 ground wire is appropriately sized according to National Electrical Code Table 250.122, which is based on the size of the overcurrent protective device protecting the circuit. For a 400 amp overcurrent protective device, a number 3 copper equipment grounding conductor is indeed adequate. Fifthly, the choice of a 4-inch conduit appears appropriate for housing the conductors and ground wire. The conduit fill requirements outlined in National Electrical Code Chapter 9 tables must be adhered to. These tables specify the maximum percentage of conduit cross-sectional area that can be occupied by conductors. The dimensions of the conductors and the internal dimensions of the conduit must be considered to ensure compliance. Using two 4/0 conductors and one number 3 ground wire in a 4-inch conduit generally falls within acceptable fill limits, but a detailed calculation should be performed using the conductor dimensions provided in National Electrical Code Chapter 9 to confirm compliance. Sixthly, the 200-foot conduit run should not pose any significant voltage drop concerns with the selected conductors. Voltage drop calculations should be performed to ensure that the voltage at the motor control center remains within acceptable limits, typically within 3% of the source voltage under full load conditions. The conductor impedance, the load current, and the length of the run are all factors that influence voltage drop. Online voltage drop calculators or hand calculations based on the conductor characteristics can be used to verify the voltage drop is within acceptable limits. Seventhly, consider the short circuit current rating of the conductors and equipment. The conductors must be able to withstand the available fault current at their point of installation. The overcurrent protective device, in this case the 400 amp breaker, must have an interrupting rating sufficient to clear the maximum available fault current. Coordination studies may be necessary to ensure that the overcurrent protected devices are properly coordinated to minimize the extent of any fault and to prevent nuisance tripping. Eighthly, the installation must comply with all applicable National Electrical Code requirements, including those related to conductor identification, support, and termination. Conductors must be properly identified by color coding or other approved means. They must be adequately supported throughout the conduit run to prevent strain on the terminations. Terminations must be made using appropriately rated connectors and according to the manufacturer's instructions. Ninthly, ensure that the equipment is properly labeled and marked. The panel board and motor control center must be clearly labeled to indicate the voltage, current, and other relevant information. Warning signs should be posted as necessary to alert personnel to potential hazards. Tenthly, consider the environmental conditions in which the installation is located. If the conduit run is exposed to direct sunlight or high ambient temperatures, additional derating may be necessary. If the environment is corrosive, conductors and equipment suitable for the environment must be selected. 11thly, verify the local electrical codes and regulations. In some jurisdictions, local codes may impose additional requirements beyond those specified in the National Electrical Code. It is essential to consult with the local authority having jurisdiction to ensure full compliance with all applicable regulations. 12thly, proper grounding and bonding are critical for safety and to minimize the risk of electrical shock. The equipment grounding conductor must be properly connected to the grounding electrode system and to all metal enclosures and equipment. Bonding jumpers must be used to ensure electrical continuity between metal parts. 13thly, consider using aluminum conductors as an alternative to copper. Aluminum conductors are often less expensive than copper conductors, but they have a lower ampacity for the same size. If aluminum conductors are used, they must be sized appropriately to meet the load requirements and derating factors. 14thly, ensure proper workmanship during installation. Conductors must be carefully pulled through the conduit to avoid damaging the insulation. Connections must be tight and secure. The installation must be inspected and tested to verify that it is safe and compliant with all applicable codes and standards. 15thly, consider the use of cable instead of conduit. In some cases, it may be more cost-effective or practical to use cable instead of conduit. If cable is used, it must be supported and protected according to the National Electrical Code requirements. 16thly, ensure that the overcurrent protective device is properly sized and selected. The 400 amp breaker must be rated for the voltage and current of the circuit and must have an interrupting rating sufficient to clear the maximum available fault current. 17thly, consider the use of energy-efficient motors and equipment. Energy-efficient motors and equipment can reduce energy consumption and lower operating costs. 18thly, ensure that the installation is properly maintained. Regular inspections and maintenance can help to identify and correct potential problems before they become serious. 19thly, document the installation thoroughly. Maintain accurate records of the conductor sizes, conduit sizes, overcurrent protective device ratings, and other relevant information. This documentation can be helpful for future maintenance and troubleshooting. 20thly, consider the use of surge protection devices. Surge protection devices can help to protect sensitive electronic equipment from damage caused by voltage surges. 21st, ensure compliance with the Americans with Disabilities Act requirements, if applicable. The installation must be accessible to persons with disabilities. 22nd, consider the impact of the installation on the environment. Use environmentally friendly materials and practices whenever possible. 23rd, obtain all necessary permits and approvals before beginning the installation. Contact the local authority having jurisdiction to determine what permits are required. 24th, use qualified and experienced personnel for the installation. Electrical work should only be performed by qualified electricians who are familiar with the National Electrical Code and local codes. 25th, verify the conductor ampacity with the manufacturer's specifications. While the National Electrical Code provides ampacity tables, the manufacturer's specifications may provide more specific information about the conductor's ampacity under certain conditions. 26. Consider the use of harmonic filters, if necessary. Harmonic filters can help to reduce harmonic distortion in the electrical system, which can improve the performance and efficiency of equipment. 27th. Ensure proper ventilation for the equipment. Equipment must be properly ventilated to prevent overheating. 28th. Consider the use of power factor correction capacitors. Power factor correction capacitors can improve the power factor of the electrical system, which can reduce energy consumption and lower operating costs. 29th. Ensure proper coordination with other trades. Coordinate the electrical installation with other trades such as mechanical and plumbing to avoid conflict. 30th. Consider the use of arc flash protection. Arc flash protection can help to reduce the risk of injury or death from arc flash hazards. 31st. Ensure proper grounding of the neutral conductor. The neutral conductor must be properly grounded to provide a return path for fault currents. 32nd. Consider the use of isolated ground receptacles. Isolated ground receptacles can help to reduce electrical noise and interference. 33rd. Ensure proper labeling of all disconnect switches. Disconnect switches must be clearly labeled to indicate the equipment they serve. 34th. Consider the use of uninterruptible power supplies. Uninterruptible power supplies can provide backup power in the event of a power outage. 35th. Ensure proper coordination with the utility company. Coordinate the electrical installation with the utility company to ensure that it meets their requirements. 36th. Consider the use of smart grid technologies. Smart grid technologies can help to improve the efficiency and reliability of the electrical system. 37th. Ensure proper training for personnel who will be operating and maintaining the equipment. Personnel must be properly trained to operate and maintain the equipment safely and effectively. 38th. Consider the use of renewable energy sources. Renewable energy sources, such as solar and wind, can help to reduce reliance on fossil fuels. 39th. Ensure proper decommissioning of the equipment at the end of its life. Equipment must be properly decommissioned to prevent environmental contamination. 40th. The plan to use 2 4/0 cables per phase and 1 number 3 ground in a 4-inch conduit for a 200-foot run to feed a 400-amp motor control center from a panel board appears to be correct, assuming that all of the above considerations are taken into account and that the installation complies with all applicable codes and standards.